thank you very much. So I will, so in my first talk, I speak about homeo, and now I will speak about diffeo. So one can, there is a kind of intersection, but they are kind of independent. So the object that I will consider is the group of diffeomorphism of a manifold. I will always suppose that the manifold is compact, that maps that are in Considerian preserve the orientation, and as I mentioned in my previous talk, but here I will emphasize that this is a group with a very nice topology, although it is not locally compact, but we would like to understand many things about this group. And what I want to emphasize is that they change a lot when you change the differentiability class. So they are really very, very different. Of course, there is something. If R is larger than S, then you have more regularity, then the group is smaller. Okay? Okay, so I think this is the right containment. So this is smaller than this. Strictly smaller. Okay. But actually, what I want to illustrate is that they have really different properties. They are algebraically different. They are even geometrically different, and so on. Let me just say, because kind of opportunity of recalling, there is a big open question on this. So this is a question by John Mather from the 80s, which is still open. So here I am considering real differentiability. So I will not deal with the reality case. If I have enough time, I will say a few words in the end. But R here is from 1 up to infinite. And all those groups, at least the connected, I will take this. It's better. The connected component of the identity. Okay? So I will avoid problems concerning the mapping class group. So all those groups are known to be simple. So John Mather proved that this group is simple for R different from the dimension of the manifold plus 1. And there is a failure in the proof in this regularity. Okay? And this is a big open question, whether in this particular class, let me call this N, whether this group is simple. Simple means algebraically simple, so there is no non-trivial normal subgroup, no proper normal subgroup. So this is an open question. Okay, I wanted to recall that this is still an open question since the 80s, and it's a kind of nightmare. So for instance, it is unknown whether this is one of my favorite problems, actually, whether the group of C2 diffeomorphism of the circle is simple. And C2 is very, very, very special. Okay? It's amazing that. So John Mather wrote 4 papers. In one paper he proved the simplicity for R larger than the critical regularity. In the other one, he realized that a modification of the proof worked pretty well for R smaller than the critical regularity. Then he wrote an article to explain why the critical regularity is so particular, it's so interesting. So there was some cohomological construction that for that particular case doesn't work. So. And in the last paper, he proved something which is very nice. So I want to record this. So in this particular regularity and in dimension 1, there is another group which is very important, not mostly from the side of dynamics, which is the group of, there is this regularity C1 plus bounded variation. So this here is bounded variation. A map is in here if it is of class C1 and the derivative has bounded variation. So if you go into the group of diffeomorphisms, this means that the derivative of the map of the diffeomorphism has bounded variation, which is the same as saying that the logarithm of the derivative has bounded variation. So I will take the logarithm of the derivative, and I have a variation for this, which is finite. It is much better to consider the logarithm of the derivative rather than the derivative. Okay? And this comes from the work of Danjois. So it's a famous theorem by Danjois, okay, who introduced this regularity in dynamics to prove that a famous somehow conjecture of Poincaré was false. So let me try to remember this. So the idea of Poincaré was the following. So he built the rotation number theory, and he realized the following problem. So you start with an irrational rotation of the circle, and you would like to construct something which is very close to a rotation, but which is not a rotation. And what he did was, well, you take an orbit, and the orbits are free, and you replace an orbit by an interval, and somehow you extend the dynamics to this new circle. This is still a circle if the length of the interval you are considering have a finite sum. And you get something which is what is called semi-conjugate to the rotation, but not conjugate to the rotation. And he understood pretty well that. So this construction, which is in general attributed to Danjois, actually comes from the work of Poincaré. And the question of Poincaré was whether such a map could be still smooth. Okay? That was his question. And it took more than 30 years to answer that question. And Danjois answered that question. He proved on the one side that one can perform this construction so that in the end one gets a C1 diffeomorphism of the circle. But no more than C1. Because in this particular class of differentiability, he proved that it is impossible. It is impossible to reach this class of differentiability. And this is one of the first results in dynamics where the regularity of the maps that are involved, it's really crucial. It's really very important. Okay? So this is why this regularity, very strange regularity C1 plus boundary variation is important. And concerning this, John Mather showed that the group of, this is very close to C2, because if the map is C2, then the variation is just the integral of the derivative of this, of the absolute value of the derivative of this. And John Mather proved that, so he gave a very clever construction showing that this group is not simple. Okay? So the question is very, very subtle. Even in dimension 1, very subtle, at least in this class of differentiability. Okay? Okay, this was just a kind of promotion of a famous open question. But I wanted to emphasize something. So these are the main object of my talk. And I would like to emphasize that these spaces as groups are different. And this is a theorem by Philip Kiewicz from the 90s, I think. It's a very nice theorem that says that if one takes a isomorphism between groups of diffeomorphisms, and isomorphism, then actually the manifolds are the same. Okay? The regularities are the same, and there is only one way to produce such an isomorphism, which is the obvious one, is to take a diffeomorphism of the manifold and to conjugate maps. Okay, so there exists a CR diffeomorphism of the manifold, well, R equal to S, such that phi of a diffeomorphism is just the conjugacy by this map. Okay? For every group, for every F, the group of diffeomorphisms. So this is a very nice theorem. It says that the group of diffeomorphism of a manifold contains all the information of the manifold. Everything. Okay? Only the algebraic structure. So here I am not asking for any kind of continuity of the map. So it's just a isomorphism as abstract groups. There are some results for maps which are only homomorphism, injective, surjective. You may ask many questions, natural questions. This were questioned by G is whether if you have a surjection, then the one of the manifold has dimension larger than the other one, and so on. There are many very nice results by Sebastián Hurtado, Catherine Mann, Frédéric Leroux, and François Militon, and so on. But essentially, the starting point of this is this very nice theorem of Filikiewicz's that actually it has a kind of larger version for the case of homeomorphism, which comes from the work of Rubin. Let me also quote the word of Rubin here. So Rubin deals with the spaces which are in the continuous category, but he deals with the spaces which are much more general than manifolds actually, even the Cantor set. Okay, and this is also a very important source of information. But this is the point. So the point is that groups of diffeomorphisms as abstract groups are different. And actually they contain the information, all of the information of the manifold. Okay, and another point of view which is close to this is, well, they are different, but they are very big. Okay, maybe we can compare them by looking at the subgroups which are inside. Okay, so the question, so the general, say, program here is, can we distinguish groups of diffeomorphisms by looking at finitely generated subgroups? And in general, it seems to be very hard, this question. So, but we have a very nice complete answer by a remarkable theorem by, I think by Kim and Coberta. Which says that the answer is yes in dimension 1. So for every R at least 1 and S strictly larger than 1. So here, let me say that, well, you can think about the exponent as integer numbers, but actually you can also consider intermediate classes of differentiability. You can think about the derivatives in some suborder spaces. This still gives groups. You can think about Holder scales in the middle and so on. But if you want to keep in mind something which is more transparent, you can think about integer numbers. But this theorem is totally general. It says that for every R squared than S, there exists a group which depends on this parameter, such that this group embeds in the larger group. The larger group is the group of smaller regularity of the interval, but doesn't embed into the larger group. And actually, they manage to do it not only for the closed interval but the circle. But actually, this is the crucial part of the. Okay, so you can distinguish the differentiability classes of these groups by looking at finitely generated subgroups, which is quite remarkable. So in general, these groups that appear are finitely generated but not necessarily finitely presented, because you have an uncountable number of parameters to deal with, and there are only countably many finitely presented groups. And what is nice also is that these groups are somehow explicit. I mean, they are not totally explicit, but there is a machine in order to build those groups, and the proof passes through a complete understanding of the difference between these regularities. Okay, which is really very, very, very interesting. Let me just say that there is after this theorem there is an alternative proof by Catherine Mann and Maxime Wolf using different ideas. But again, this is a complete answer to that question in dimension 1, and in higher dimension this seems to be very okay. So, as I said this morning, this theory, this general understanding of group of transformations works really well in dimension 1, but in higher dimension there are many actually very naive open questions. So let me state one question, maybe illustrate this. This is, for me, this question is a kind of shame. I mean, we are unable to answer such a simple question. Okay, and the question is the following: does there exist gamma finitely generated and torsion-free such that gamma doesn't embed into the group I think of, even for this case, homeomorphism of the two sphere. Okay. So it is, in dimension 1, we have reached a number of invariant kinds of abstraction to embed a group inside, but in dimension 2 it's very, very hard to get. Yeah, this is an open question. Maybe it's more natural to state it for the case of the torus, but this is an open question. So what I wanted to emphasize is that we have no general abstraction to embed a group inside homeomorphism of a two manifold. But in the previous talk, I showed you that there is an abstraction to embed into homeo of a one manifold, at least for the interval or the real line, which is a property of being left orderable. But here, nothing like such a property is known. Okay, and what I want to discuss now is whether we can compare or whether we can study these groups, which are enormous, geometrically. So this is the question. Can we study this group geometrically? And again, these are very, very nice questions, but they are very interesting. I mean, kind of alternative point of view for doing dynamics. So dynamics means, in general, classical dynamics means that you take a diffeomorphism and you start looking the iterates of the diffeomorphism, and you see what happens, and you see what happens in the manifold. And what about if you change the question? Instead of looking what happens on the manifold, you look at what happens in the loop. Okay? And getting some information starting from that. Well, this approach actually is not new. So there is a point of view of like this in the work of Arnold. on diffeomorphism preserved in the volume. Okay, inspired by questions that come from physics. Okay. Okay, but the point is that actually we think a little bit. So geometrically means what? Taking some distance, taking something. So in group theory, it is very good to consider what are called length functions. What is a length function? It's a function from the group into the reals that satisfy this property of subadditivity. So we would like to have this. This is a length function in a group. And actually, this question passes through the understanding of what are the length functions that one can define on groups of diffeomorphisms. Okay? And let me give you an example that will clarify this, and that will clarify as well the relation with dynamics. Okay? So suppose that we are in class C1. We know that if we change the regularity, the groups are very different. So there should be length functions that are adapted to the corresponding differentiability class. But let's suppose that we are in class C1 and M is any manifold, say compact. Well, for this case, there is a length function. So you take L of f equal the logarithm of the norm of the derivative, but the norm in the continuous setting. So the sum of the norms of the derivatives, and you take the logarithm. This is a length function because of the chain rule. This is a length function. Okay. Question: are there any other length functions? Amazingly, this is very hard to answer. Okay, and so far I think that so far there is no general answer. The answer is yes for in dimension 1. This is a theorem by. This is a quite recent theorem actually, but this kind of questions are very hard to answer. So let me just say something. When you have a length function in a group, there is a procedure to consider what is called the stable version of the length function. So because of this inequality, we have that for every element in the group, the length of f to n plus n is smaller or equal than the length of f to the n plus the length of f to the n. Okay? And whenever you have this inequality, there is a classical lemma by Fekete that says that, and there exists the limit of L of f to the n divided by n. This is totally general. If you have a length function, then you have this, and you can call this, say, L infinite. The stable version, the stabilization of the length. So it may happen that the length of an element is positive, but the stable length is. For instance, in this case, L infinite of f, well, this is the logarithm of the derivative of n divided by n, is somehow the Lyapunov exponent. Okay? This is called, what is called the maximal Lyapunov exponent. Okay? And so with this approach, somehow you recover this classical object in dynamics. And well, why this question of detecting length functions on groups of diffeomorphism is difficult? It is because it is known to be difficult to build a theory of Lyapunov exponent in high regularity. This is kind of a nightmare in dynamics. Okay? So this is difficult, but I can still state a couple of questions without knowing exactly what are the length that are very concrete on groups of diffeomorphisms. Okay, so let me remind you a definition. This was proposed by Gromov in the 80s, and is the following. So suppose that gamma is a finitely generated group, and let F an element in gamma. So I fix a system of generators in gamma, okay? And I consider a group element. So F is distorted if the following, well, let me remind you something. When we have finitely generated groups, there is a length which is obvious. You fix the system of generators, say G1 up to Gk, and you denote. Well, this is Gromov's notation. So the norm of F, well, the length of F, or the norm of F, is the minimum value, minimum number of generators that you use in order to write the element. Okay, the minimum number of factors that you use among these generators. I suppose that the generated system is symmetric, so that I can use only positive powers. Okay? And this is a length. Okay? And of course, it depends on the system of generator, but if you change the system of generator, this length doesn't change too much. So the definition by Gromov is the following: say that F is distorted if the corresponding stabilization of the norm for F vanishes. If the limit of the norm of F to the n divided by n equals to C. Okay? This is a distorted element in the group. It's an element for which the powers may go to infinite. So I will assume that F is not a torsion element. So the powers go to infinite, but they go slowly. They don't go at a linear rate. They go at a sublinear rate. And there are many examples of this. For instance, if you take an abelian group, this doesn't happen. But if you take an impotent group, this arises immediately. This is the key point in Gromov's theorem of the characterization of impotent groups in terms of polynomial growth. Okay, but for me, there is another example that I like very much, and you will see why this is so nice. So this is the bound-arc solitaire group 1, 2. Okay, so the bound-arc solitaire group 1, 2 I will take as the group generated by two elements, such that one of them conjugates the other to its square. Okay, this is the classical presentation of bound-arc solitaire. Okay, what I will say works pretty well for all solvable bound-arc solitaire groups, but let me keep this in mind. So this is a group of affine transformation and sits inside the group of Möbius transformation. So there is a very, very simple realization as a group acting on the real line. So you may think as F as the map as a translation, say by 1, doesn't matter, and G the multiplication by 2. And you will get this relation. So this is. And the point is that in this group, this element F is distorted. Okay? And the reason is that if you take this conjugacy and you conjugate again by G, you get the conjugate of F to the square, which is F to the 2 to the 2. So in general, if you conjugate F by G to the n, you get f to the 2 to the n. Okay? And this means that the length of f to 2 to the n is much smaller than the exponent. It's smaller or equal than 2n plus 1. So if you divide by the exponent, you get 0. So this is a distorted. This is actually the largest distortion you may have in a group. This is what is called exponential distortion. Okay? Good. So we have an example of a distorted element, and we have an example of inside a group, which is naturally a group of transformations. So now there is a more general definition. If you want to deal with groups which are not necessarily finitely generated, Gromov proposed the following definition. Let G any group say that an element in G is distorted. Before that, so the length of the group element depends on the system of generators, but the property of being distorted doesn't depend on that, because if we change the length, well, they will change in a Lipschitz way. So, okay, so a group element inside any group, there is no geometry a priori in this group, but you will say that an element is distorted if it is distorted inside some finitely generated subgroup. Okay, and this may seem a very weird definition, and you may think, well, with such a definition, maybe everything is distorted, because if the group is very big, maybe one can manage to produce, given an element, one can manage to produce generator of a finitely generated subgroup so that everything becomes distorted. Okay, so this is an exercise. So it is, I think it is unpublished. It is a very nice remark by Yves de Cornoulier. So it requires a proof actually, but it is unpublished. It's really a pity. Is that if you take, this group is very interesting, the group of homeomorphism of the Cantor set. So this is an example of a very big group. Why it is interesting? It is because every countable group sits inside the group of homeomorphism of the Cantor set. This is, you think a little bit, if you take, say, if you take gamma, any countable group acts on this product just by shifting coordinates. And if gamma is infinite, this is a Cantor set. So every group sits inside the Cantor set, the group of homeomorphisms of the Cantor set. So if you think things dynamically, you may think that all the group theory is okay. And actually, this may seem very naive, but actually many important groups have been discovered as group acting on the Cantor set. Okay, so what Yves notices is that in this group, every F is distorted. It's a very nice argument. It is not obvious, but not very surprising, because this group is really very large. But again, let me go to the case of diffeomorphism of manifolds to show you why some elements cannot be distorted. So take G, the group of C1 diffeomorphisms of any manifold, but C1, and take F in G with an hyperbolic fixed point. Then F is undistorted. Okay? Why is that? Well, a direct way to think about this is the following. So if you have a fixed point, then if you iterate f, it remains in the same position. But if it is a hyperbolic, the derivative grows exponentially, so that the logarithm of the derivative grows linearly, so that it is impossible to write the powers of this element as product of a smaller number of generators. Otherwise, the logarithm of the derivative will grow sublinearly. A more transparent argument is to consider the length function L, which sends an element in G into the logarithm of the derivative of the norm, into the logarithm of the norm of the derivative. So this is a length function, and for an element like this, the length function grows linearly, because this norm grows exponentially and the logarithm grows linearly. But since this is a length function, if you write, say, f as a product of generators, f to the n as a product of generators, then L of f to the n should be smaller or equal than the sum of L along the generators that you are using. And this is a finite number of there are a finite number of generators, so there is some constant times the number of generators you are using, so that if you divide by n, you have this inequality, and if k is much more smaller than n, then you have that this converges to 0. So if the element is distorted, which corresponds to this property, then the stable version of this length function has to vanish. Okay? And this is not the case if you have a hyperbolic fixed point. Okay, so in the C1 category, you see that again this notion is capturing something. This notion of distortion is capturing something. Actually, one can prove more. So this is a very particular case, but actually one can show that this is not exactly a theorem. This is a proposition. Also, this is a remark. This is not very hard. Is that if f is distorted in the group of C1 diffeomorphisms of a manifold, then the topological entropy of f vanishes, which is also very interesting, because one can construct examples of maps, for instance, on the torus that have no periodic point at all. They are like rotations, but they are what are called pseudo-rotations. They are not really rotations, but they have no periodic point at all, and they have positive entropy. And this result, which is really very elementary, shows that this element cannot be, this diffeomorphism cannot be expressed as distorted element. Cannot be distorted in the group of C1 diffeomorphism. So there are also very nice constructions. So let me state two of them. So there is a theorem by Artur Avila, a very nice construction that says that for every irrational angle, the rotation by this angle is distorted in the group of C infinite diffeomorphism of the circle, which is really very nice. So for every rotation, one can create finitely many diffeomorphisms of the circle, so that using very smart algebraic identities, one can express powers of the rotation as products of a very small number of generators. Okay. So by the way, this is not to hold in the C infinite category, but it is unknown in the real analytic category. So this is one of the of the naive on this stuff. Okay. And there is another theorem that says that the same holds. Well, this is a kind of complement. Well, this is by Zarek and collaborators. It says that the same holds in the group of piecewise affine homeomorphism of the C. This is also very nice. This is not just a modification of Arthur's technique. This is really, there are some combinatorics inside. And this is really very nice. So one can produce now finitely many, given an irrational number, an irrational angle, one can produce finitely many homeomorphisms, which are piecewise affine, so that we can do these tricks in order to express the powers of this rotation as a product of a small number of generators. Okay, these are examples. There are many. There is an extension of this by Militon and so on. But let me state now a general question. So the general question is the following. It's like in the spirit of the theorem of Kim and Coverda, that I like very much. So given R, again, smaller than S, so does there exist a diffeomorphism of class CS and given a compact manifold? Okay, say this, such that first thing, F is distorted in the larger group and F is undistorted in the smaller group. So is it possible to differentiate groups of diffeomorphisms just by looking at distorted elements? So my guess is that this should be possible. But again, I like this question because what is behind this is the question that I stated before about the understanding or the eventual classification of length functions on groups of diffeomorphisms. Okay? And here, in general, the most difficult thing is to prove non-distortion. Because to prove distortion, you have a map, and you would like to express this map as a. You would like to find finitely many elements in the group so that you can express the powers of the map as products of a small number of generators. Okay, this seems to be doable. I mean, this is what these guys did in the case of rotations, and okay. But proving non-distortion requires that being able to prove that this cannot be done. And the only thing that we know is the following: the thing that I illustrate with that argument, but it is totally general. If L is a length on a group, it's a length function, and F is distorted, then the stable version of L at this element has to vanish. Okay? This is the point. Okay? This is essentially the argument that I gave there. It's totally general. It has to vanish. Okay? So in order to prove undistortion, we really need to build length functions on groups of different. This is so examples of length functions. Well, I gave one in in any dimension. This is the logarithm of the norm of the derivative. And in dimension 1, this case is very nice because we have many other length functions. Okay, and this is so in dimension 1 there is the logarithm of the derivative. This comes from the chain rule. Yes. So this is dg times df composed with g. So if you take the logarithm, which is much better, you have this. Here these are just numbers. So if you take an element f and you send it into the logarithm of the derivative, the sup of this is a length function. But there is another chain rule in dimension 1. For higher regularity, there is the chain rule for another derivative. Actually, there are 3 derivatives in dimension 1. There is this derivative, the classical derivative, or what is better, the logarithm of the classical derivative. And there is another derivative, which is the derivative of this. If you take the derivative of the logarithm of the derivative, then you get, okay, let me write this. D log d fg equals d log the derivative of g plus, here there is a composition, so this is d log df composed with g times dg. Okay, well, the derivative of the logarithm of something is d2 over d. And this is what is called the affine derivative, because this vanishes if and only if this is constant. So if and only if the derivative is constant. So if and only if the map is affine. Okay, so you have this equality, d2 over d of g plus d2 over d of f composed with g times dg. Okay? Good. But there is this expression here, which is bad. So if I take the sup, it doesn't work because there is this derivative. So I will not take this. So I will not take exactly the C2 topology, if you wish. Or I will not consider a length that captures the full of the C2 topology, but something very close. Instead of taking the sup, I will take the L1 norm of this. If I take the L1 norm of this, because of the triangular inequality, will be smaller or equal than the L1 norm of this, and the L1 norm of this. And here you see you interpret this as a change of variables. So you have that the L1 norm of the affine derivative of the composition is smaller or equal than the L1 norm, than the sum of the L1 norms of the affine derivatives. So we have a length function. Okay, thanks to the affine derivative. And believe me, this is something that we already appeared in this talk. So let me come back to this. Let me go back to Earth. Okay. So the norm of this L1 norm is the integral of the absolute value of this. Yeah? The integral of the absolute value of this. And this is, for a map, for instance, which is of class C2, this is the variation of the logarithm of the derivative. So we retrieve the variation of Danjois this way. But, well, there is something which was much more transparent, actually. Is the fact that the variation of the logarithm of the derivative of the composition is smaller or equal than the sum of the variation of the logarithm of f plus the sum of the variation plus the variation of the logarithm of f. Okay. Okay. You can think both ways. So as the variation of the logarithm of the derivative or as the L1 norm of the affine derivative. And this gives you a length function which lives in higher regularity. This is higher than C1. But this is very particular for dimension 1. There is nothing there is no, well, it is a theorem actually by Bruno Sevenek that there is nothing like the variation of the logarithm of the derivative in higher dimension. Of course, you can define the variation of a function, but what is nice also with the in dimension 1 is this invariant on the exchange of coordinates. And in higher dimension, this cannot exist actually. It's a theorem by Bruno Sevenek. But we have a length function, so it is not very surprising that using this length function, one can prove something. And this something is the only answer that I know for that general question about distorted diffeomorphisms. The only answer, say non-trivial answer. So the answer is for a case where M is the closed interval. It doesn't work, unfortunately, for the case of the circle. And R equals to 1 and S equal to 2. Okay? So the answer is there exists a C2 diffeomorphism of the circle, of the interval, sorry. Actually, the diffeomorphism of class C infinite. And there are many. It is distorted in the group of C1 diffeomorphisms. And it is undistorted in the group of C2 diffeomorphisms. And how do I prove undistortion? Is using this length function and the corresponding stable version. How do I prove distortion? Well, it's doing computation by hand. So I have a candidate, and okay. But the point is that understanding what is the associated stabilization of the length function in class C2 is very interesting. It is related to some objects that were already classical in dynamics, but with this point of view, we retrieve this object. Let me just say that there is an extension that it was really a surprise for me, that this can be done not only in class C1, well, this may seem very technical, but this, in any class of regularity, C1 plus holder, for any holder exponent is smaller than 1. Okay? But so far, this is the only thing that we know how to produce. This is very explicit, actually. And actually, the examples here are quite related to the bounds-like solitary groups. So in these groups, there are some regions where one see the bounds-like solitary relation in many places. But as you may imagine, this is really very technical. And again, this only differentiability 1 and 2. We don't know what to do with differentiability with the class C3, for instance. And higher than C3, then we have no idea. So there is some hope of doing something similar in class C3 because there is another derivative, another classical derivative in dimension 1, the projected derivative, also called the Schwarzian derivative. You know, there is this very awful formula, which is, okay, d3 over d of f minus 3/2 d2 over d of f to the square. Okay? And this vanishes only for Möbius transformations. And this satisfies a chain rule. Okay? This is the Schwarzian of the composition is the sum of the Schwarzian with a twist. But now the twist is not given by the derivative, but by the square of the derivative. And well, using this, one can produce a new length function. It is not that clear because I cannot do the trick of taking the norm of this in L1. I have to do something else. Okay, and At least I can produce a length function. However, I am not able to build something like this that differentiated class C1 and class C2. But let me just finish by explaining how to produce another length function, okay? In order to illustrate why playing with derivative gives some geometric information on this. So the Schwarzenegger derivative is not totally suitable for doing that because it is a quadratic differential. But there is another formula that I like very much. So this is really a fantastic formula. Okay, it is better, and this is very well known in physics actually, but in representation theory as well, to see the Schwarzenegger derivative well, this is a function, but actually as a function in two variables. So it is better to look at the following expression. So you take the derivative of a map at 2 points, you divide by this, and well, there is a singularity here if you see, okay, along the diagonal. But if G is regular enough, because well, there is a singularity here, and if G is regular enough, these two singularities actually cancel each other. And there is a very nice formula. So the limit when y goes to x of this, I think you have to put 1/6. Maybe I'm wrong, maybe you have to put 6, but I think the 1/6 is okay. So what you get is the Schwarzenegger derivative of G. Okay, this is a very nice formula. And I like pretty much this formula because, for instance, showing this equality it's a computation. It's not that easy. But if you see this expression and you see this equality, if you see this expression, this becomes obvious. Why there is a square in this formula? Because here actually you are multiplying. And what is interesting is that if you look at this as a function, say I will call this function C because it's a cosine. It's another kind of function. As a function in two variables, then I have this equality. This is equal to, I think, C of f at the points gx, gy times the derivative of the product of the derivatives plus this. Okay, and passing to the limit this equality, you get the relation for the Schwarzenegger derivative. Okay, this is important. But what is nice with this is that now you can play the game of the L1 game, because here again you have a change of variables, but in the space L1 of the product of the circle with itself. So I look at the norm of this in L1 of the product. And because the change of variable, the norm that I get here is the norm of CF plus the norm of CG. Okay? So that this is a length function that captures somehow the third derivative of the map. It is not exactly the third derivative, but it is the third derivative of the map. These are kind of very, very nice construction, but well. Okay, it's a kind of nightmare to me. So, is there something that says that maybe it is impossible to capture higher regularities using length functions? Maybe it is possible, and we don't have the good derivative, the good invariance. Okay, but this is the question. Can we detect, for instance, can we construct a length function that detects this derivative? Okay, that really detects this derivative, because of course you can consider all these functions in this loop, but that detects this derivative, I don't know. So a length function here, even in dimension 1, and here to R. Okay, have no idea. Okay, I think it's enough. Thank you very much.